China's mega projects are changing Africa's future. You're watching China reshape an entire continent with 16 mega projects that most people have never heard of. We're talking about bridges that span impossible distances, power stations generating enough electricity for millions, and ports that will redefine global trade routes. These aren't plans on paper. They're already built, already operational, already transforming how 300 million Africans live their daily lives. And the engineering behind them is unlike anything the continent has ever seen. But before we get to the railways connecting landlocked nations to the sea, there's a city rising from the Egyptian desert that makes Dubai look modest. New administrative capital, CBD. $45 billion being poured into empty desert east of Cairo. The new administrative capital's central business district is 20 skyscrapers, including Africa's tallest building, erupting from sand where nothing existed 5 years ago. The iconic tower stands over 2,000 feet tall, with 80 floors overlooking a city designed for 6.5 million people. China State Construction Engineering Corporation built an entire urban core with its own metro system, power grid, and water infrastructure from absolute zero. 60,000 workers on site simultaneously. Foundations going 20 stories deep into desert bedrock, while surface temperatures hit 130 degrees Fahrenheit. The iconic tower needed over 300,000 tons of steel reinforcement, more than the Eiffel Tower's entire structure. Dedicated batch plants produced concrete 24 hours a day for 3 straight years. They built substations delivering 500 megawatts just to keep construction running, then engineered a permanent grid handling 2 gigawatts at full capacity. 7 years from desert to functioning capital district, half the time conventional engineering said was possible. But 100 miles west, an even more audacious project was taking shape on the Mediterranean coast, Alamein Downtown Towers. $6 billion to build a city on a beach. China Fortune Land Development Corporation constructed 33 towers on empty Mediterranean coastline where absolutely nothing existed. The centerpiece rises 800 feet, engineered to survive salt air, hurricane-force winds, and foundations built entirely on sand. Every tower required pile foundations driven 200 feet deep through loose coastal sand to bedrock. The main tower alone needed over 4,000 individual piles, each reinforced with steel cages and filled with high-strength concrete mixed to resist saltwater corrosion for a century. Alamein Downtown had 0 existing utilities. China's engineers constructed desalination plants producing 8 million gallons of fresh water daily, power grids handling 300 megawatts, and sewage treatment processing millions of gallons daily. 4 years from bare sand to functioning city, they poured foundations for all 33 towers simultaneously, coordinating 200 mixer trucks running around the clock. The steel reinforcement totaled over 150,000 tons. A complete urban center for 400,000 residents, engineered faster than most cities build a single skyscraper. But creating cities from nothing is just the beginning. Wait until you see what they engineered for worship. Great Mosque of Algiers. $1 billion to build the world's tallest minaret in one of the most seismically active regions of the Mediterranean. The Great Mosque of Algiers rises 869 feet taller than any religious structure on Earth and sits directly on a fault line. China State Construction Engineering Corporation built a structure that flexes during earthquakes without collapsing while holding 120,000 worshippers inside. The minaret's foundation goes 130 feet deep, anchored by over 600 massive piles drilled into bedrock. The entire structure uses base isolation technology, giant shock absorbers that let the building slide horizontally during seismic events. The bearing pads handle lateral movements of 3 feet while supporting 40,000 tons above them. The prayer hall spans 300,000 square feet of column-free space under a dome 200 feet across. The dome alone weighs 12,000 tons. At 869 feet tall, wind loads become exponential. China's engineers designed a tuned mass damper, a 600-ton counterweight that moves opposite to wind-induced sway, keeping the structure stable in winds exceeding 100 miles per hour. 7 years of construction and a structure that defies both gravity and geology. But building vertically is one challenge. Spanning horizontally across water is an entirely different engineering beast. Maputo, Katembe Bridge. $400 million to span 1.8 miles of open water in Maputo Bay. The Maputo Katembe Bridge is Africa's longest suspension bridge, built where currents rip through at 6 knots and water depths hit 200 feet. China Road and Bridge Corporation engineered this in conditions that would sink most construction equipment. The two main towers rise 500 feet above water. Each tower sits on a foundation caisson, massive concrete boxes filled with over 30,000 cubic yards of concrete each, positioned with millimeter precision while fighting powerful currents. The main cables span 1.8 miles, each woven from thousands of steel wires with a combined breaking strength of 120,000 tons, enough to suspend 60 fully loaded cargo ships. The bridge deck isn't rigid, it's designed to flex. Mozambique gets cyclones with winds exceeding 130 miles per hour. The deck segments can move vertically up to 16 feet and sway laterally over 6 feet without structural damage. Each of the 147 deck sections weighs 200 tons and was lifted into place by specialized cranes operating from barges in open water, 4 years from first pile to opening day. But China wasn't done bridging African waterways. Lagos needed something even more audacious. Lekki-Ikoyi Link Bridge, $250 million to connect Lagos across a mile-wide lagoon. The Lekki-Ikoyi Link Bridge is a cable-stayed monster 3 towers rising 330 feet above water, handling 60,000 vehicles daily. China's Civil Engineering Construction Corporation built this in water churned by tides, with foundations punching through 60 feet of soft lagoon mud to reach solid-bearing soil. Each tower foundation required over 200 driven piles, each going 130 feet deep. The cable system uses 76 individual stay cables per tower, each pre-tensioned to exact specifications. If even one cable is tensioned wrong, the entire deck geometry shifts. The cables carry loads of over 3,000 tons each. The deck is a steel box girder, 53 individual segments, each weighing up to 400 tons, lifted into place and welded together while hanging from cables. Segments had to align within half an inch over spans exceeding 800 feet. Wind loads hit 90 miles per hour during rainy season, so the deck was engineered to oscillate up to 10 feet vertically without creating destructive resonance. 3 years from lagoon bed to opening. But bridges move people, railways move economies, and Nigeria's economy was about to get its backbone rebuilt. Lagos-Ibadan Railway, $1.5 billion to resurrect a railway corridor built in 1900. The Lagos-Ibadan Railway runs 103 miles, and China Civil Engineering Construction Corporation converted it from narrow gauge decay into standard gauge modern rail in 4 years. This isn't just laying track, it's engineering for speeds of 100 miles per hour through terrain that floods and requires over 60 bridges. The track uses continuous welded rail quarter-mile-long sections welded together to eliminate joints that limit speed. The rail bed required 40 million cubic yards of ballast and subballast, graded to tolerances of less than 1 inch over 30-foot spans. They built 12 stations from scratch, each handling 15-car train sets carrying over 2,000 passengers. The bridges, 63 of them. The longest crosses 1,500 feet using pre-stressed concrete box girders cast on site, lifted by gantry cranes and positioned with hydraulic jacks while surveyors verified alignment to within millimeters. Each bridge pier foundation goes 70 feet deep to avoid seasonal flooding. The signaling system uses Chinese train control technology automated systems communicating with trains in real time. Travel time dropped from over 6 hours to 2. Capacity jumped from 300,000 passengers annually to 15 million. But moving people is one thing. Generating power to run an entire nation is where China's engineering gets truly massive. Mambila Hydroelectric Power Project. $5.8 billion to dam the Donga River and generate 3,050 megawatts enough electricity to power 8 million homes. The Mambila Hydroelectric Power Project is 4 separate dams cascading down the Mambila Plateau. China Gazuba Group is engineering reservoir systems that will flood over 150 square miles. The main dam rises 330 feet, holding back a reservoir containing 4 billion cubic yards of water. Foundation excavation required blasting through 2 million cubic yards of volcanic rock to reach bedrock. They're pouring over 6 million cubic yards of roller-compacted concrete layers compressed by 30-ton vibrating rollers to resist water pressure equivalent to 30 atmospheres at the base. The real power generation happens in underground powerhouses carved into solid rock. Each powerhouse is a cathedral-sized cavern, 500 feet long, 80 feet wide, 150 feet tall, excavated 200 feet below ground. Inside, 12 massive turbine generator units, each producing over 250 megawatts. Water drops through penstocks 16 feet in diameter, creating enough pressure to spin turbine blades at 200 revolutions per minute while handling flows of 20,000 cubic feet per second. Construction timeline: 8 years. And Mambila is just one of 4 hydroelectric giants China's building across Africa right now. Kakulo Kabasa Hydropower Station. $4.5 billion to harness the Kwanza River in Angola and generate 2,172 megawatts. The dam rises 430 feet, creating a reservoir stretching 93 miles upstream. Foundation excavation went through 130 feet of river sediment and fractured rock before hitting gneiss bedrock. The dam uses 5.2 million cubic yards of roller-compacted concrete, poured in continuous 3-foot lifts around the clock for 3 years. Angola's rainy season is brutal. The Kwanza River's flow can spike from 20,000 cubic feet per second to over 300,000 in hours. The spillway system has 6 radial gates, each 65 feet wide, that can discharge 1.2 million cubic feet per second when fully open. Underground, 6 turbine generator units sit in caverns blasted from granite. Each Francis turbine is 30 feet in diameter, extracting maximum energy from water falling through penstocks at pressures exceeding 400 pounds per square inch. 6 years from first excavation to grid synchronization, Angola's power output doubled overnight. But China was already engineering an even more complex project in Zambia's Kafue Gorge, Kafu Gorge Lower Hydropower Station. $2 billion to build a second dam in Zambia's Kafue Gorge, just 9 miles downstream from the existing Kafue Gorge Upper Station. The Kafue Gorge Lower Hydropower Station generates 750 megawatts. China's Sinohydro engineered this in a canyon where there's already a massive dam upstream controlling flow. The dam is 315 feet tall. The Kafue Gorge is solid basalt volcanic rock so hard it shatters drill bits. They excavated 1.8 million cubic yards, blasting 24 hours a day for 18 months just to reach stable bedrock. Then they poured 3.1 million cubic yards of concrete using an overhead cableway system, placing 300 cubic yards per hour. The powerhouse contains 5 turbine units, each generating 150 megawatts. The turbines were designed for highly variable flow rates. Upstream releases change hourly based on grid demand. They use adjustable guide vanes and runner blade angles that optimize performance across a 3-to-1 flow range. The penstocks are 42 feet in diameter, lined with steel plate 3 inches thick to handle pressure pulses. 4 years to completion. Zambia's grid capacity increased 40%, and Uganda was about to get the same treatment on an even larger scale. Karuma Hydropower Station. $1.7 billion to dam the Victoria Nile and generate 600 megawatts. Karuma Hydropower Station conquers one of the Nile's most violent sections where the river drops 130 feet through a granite gorge. China's Sinohydro had to build in active whitewater, divert a river carrying 170,000 cubic feet per second without flooding communities upstream or starving Lake Albert downstream. The solution was a cofferdam system redirecting the Nile through temporary channels blasted into canyon walls. The main dam rises 115 feet, a run-of-river design with just enough height to create hydraulic head for turbines. They poured 1.6 million cubic yards of concrete, engineered to let most of the Nile's flow pass through turbines rather than spillways. The real engineering is underground. 6 turbine generator units sit in a powerhouse cavern 600 feet long, carved from solid granite, 200 feet below ground. Excavating required 800,000 cubic yards of rock through drill and blast and tunnel boring. Each turbine is a Kaplan-designed propeller blades that adjust pitch in real time to match varying river flows, generating 100 megawatts even when the Nile's running at 50% of average discharge. 6 years from river diversion to first power generation. Uganda's electricity supply tripled. But power is useless without infrastructure to move goods. And Lagos was about to get Africa's most advanced port, Lekki Deep Sea Port. $1.5 billion to build West Africa's first fully automated deep sea port. The Lekki Deep Sea Port is China Harbor Engineering Company's solution to Nigeria's shipping bottleneck, a port handling 18,000 TEU container ships, too massive for every other West African facility. The challenge: building in coastal swamp, dredging a turning basin that constantly refills itself, and constructing quay walls surviving both ship impacts and the Atlantic Ocean. They dredged 15 million cubic yards to create an approach channel 52 feet deep and a turning basin over 3,000 feet across. The channel walls are lined with rock armor, individual boulders weighing up to 15 tons, in interlocking patterns that dissipate wave energy. The main breakwater extends over 5,000 feet, built from 8 million tons of quarried rock stacked from 30-ton core stones to 500-pound surface armor. The quay wall uses concrete caisson structures, hollow concrete boxes, each 300 feet long, 80 feet wide, 65 feet tall, weighing 25,000 tons. Built in a dry dock, floated into position, sunk onto prepared foundations and filled with sand, 24 caissons create a continuous berth over 4,000 feet long. Behind them, 80 automated gantry cranes lift 65 tons and stack containers 9 high, with positioning accuracy measured in inches. Capacity: 2.7 million TEU annually, with expansion plans to quadruple that. Construction took 5 years. Nigeria's port capacity doubled. But ports need cargo to justify existence, and East Africa's railways were about to deliver exactly that. Mombasa Nairobi Standard Gauge Railway, $3.8 billion to connect Kenya's coast to its capital across 293 miles. The Mombasa Nairobi Standard Gauge Railway replaced a colonial-era narrow gauge line that took 12 hours. China Road and Bridge Corporation built standard gauge designed for 75-mile-per-hour passenger trains and 50-mile-per-hour freight, cutting travel time to 4 hours and multiplying cargo capacity by 6. Crossing the Savo region means bridges over ravines where elephants migrate, viaducts through national parks, and cuttings through bedrock requiring blasting 2 million cubic yards of granite. They constructed 98 bridges, the longest spanning 3,000 feet across the Athi River, using pre-stressed concrete box girders cast in segments. Every pier foundation goes at least 40 feet deep to avoid seasonal flooding. They built it in 2.5 years. That's laying over 300,000 concrete sleepers, installing 12,000 tons of continuously welded rail, grading 22 million cubic yards of ballast and sub-ballast, while coordinating with wildlife authorities to avoid disrupting animal migration. The trackbed uses geotextile fabric and drainage systems surviving Kenya's rainy seasons that dump 6 feet of water in 3 months. The signaling system is full Chinese train-controlled GPS-based positioning, with automated speed regulation managing 60 trains simultaneously. Freight capacity jumped from 1.5 million tons annually to 22 million. And Kenya's railway ambitions didn't stop at Nairobi. They needed a line reaching landlocked neighbors deeper in the continent. Addis Ababa Djibouti Railway, $4 billion to connect landlocked Ethiopia to the Red Sea across 470 miles of hostile terrain. The Addis Ababa Djibouti Railway is Africa's first fully electrified transnational standard gauge railway designed for 75-mile-per-hour passenger service through desert, mountains, and the Great Rift Valley. Here's the engineering nightmare. Addis Ababa sits at 8,000 feet above sea level. Djibouti is at sea level. That's an 8,000-foot descent over 470 miles. They bored 43 tunnels, the longest stretching nearly 10 miles through the Elejo Mountains. Then came 150 miles of track across the Afar Depression where temperatures hit 130 degrees and the ground is salt flats that expand and contract with temperature swings. The trackbed uses concrete sleepers with thermal expansion joints every 30 feet to prevent buckling. The electrification system overhead catenary wires, carrying 25,000 volts, required over 6,000 support gantries, engineered to withstand thermal expansion and wind loads, where dust storms create TU. Near zero visibility. They built a completely independent power supply system because neither Ethiopia nor Djibouti had grid capacity for an electrified railway. 6 years to completion, Ethiopia's freight costs to the coast dropped 70% and travel time from 14 hours by truck to 12 hours by train. But while railways connected nations, Kenya's capital needed something to fix the daily nightmare of urban traffic: Nairobi Expressway. $670 million to build an elevated toll highway cutting through Nairobi's worst traffic corridor. The Nairobi Expressway is 17 miles of elevated roadway built by China Road and Bridge Corporation in just over 2 years, a 6-lane divided highway running 50 feet above existing streets, moving 70,000 vehicles daily without touching the chaos below. The structure uses precast concrete box girders built off-site, trucked in at night, and lifted by massive gantry cranes that straddled existing traffic. Each girder segment weighs up to 100 tons and spans 130 feet between support columns. They installed over 3,000 segments, working 24-hour shifts. The support columns punch through Nairobi's urban infrastructure sewers, power lines, water mains requiring excavations up to 65 feet deep to reach stable soil. But here's the achievement. They built this while keeping Nairobi's main artery operational. Construction sequencing was surgical excavate column foundations at night, pour concrete before morning rush hour, install girders on weekends. The toll system is fully automated RFID tags and license plate recognition processing vehicles at highway speeds without toll booths. Commute times drop from 2 hours to 15 minutes. But East Africa needed more than urban expressways. It needed deep water ports to handle the cargo those railways were bringing to the coast. Kribi Deep Sea Port. $1 billion to build Central Africa's first deep water port on Cameroon's Atlantic coast. The Kribi Deep Sea Port is China Harbor Engineering Company carving a container terminal. From mangrove swamps where water depths naturally hit only 30 feet, nowhere near enough for modern container ships needing 52 feet minimum. They dredged 12 million cubic yards of seabed to create an approach channel and turning basin, then built breakwaters extending 4,000 feet into the Atlantic. The main breakwater uses 7 million tons of quarried rock core stones up to 20 tons each, stacked and interlocked to dissipate wave energy from storms generating swells exceeding 20 feet. They constructed quay walls using caisson technology. Massive concrete boxes floated into position, sunk onto prepared foundations, and filled. Each caisson weighs 18,000 tons. 15. Create a continuous berth stretching 3,000 feet. Behind the quay, the terminal yard covers 150 acres of land reclaimed from swamp by dredge and fill operations, moving 8 million cubic yards. The container handling equipment includes 12 ship-to-shore gantry cranes, lifting 60 tons and reaching across ships 23 containers wide. The yard has capacity for 1.2 million TEU annually, with rail connections moving containers directly from ship to inland destinations without truck transfers. Construction took 4 years. Cameroon went from zero deep-water port capacity to handling the largest container ships operating in the Atlantic. But Tanzania was planning something even more ambitious on the Indian Ocean, Port of Bagamoyo. $10 billion to build what would become Africa's largest port 60 miles north of Dar es Salaam. The Port of Bagamoyo is China Merchants Holdings' plan to create a container terminal handling 20 million TEU annually, more than any port in Africa currently processes. This isn't just a port. It's an industrial zone covering 12,000 acres with dedicated rail connections and berths designed for the absolute largest container ships afloat. 24,000 TEU megavessels, requiring water depths of 65 feet. The dredging operation would move over 30 million cubic yards of seabed material to create approach channels, turning basins, and berthing areas deep enough for ships drawing 52 feet loaded. The breakwater system extends over 3 miles into the Indian Ocean, requiring 20 million tons of quarried rock protecting the harbor from monsoon swells and cyclones. The main container terminal uses caisson quay walls, over 100 individual concrete boxes, each 300 feet long and 70 feet tall, creating continuous berths stretching 4 miles. Behind those berths, the terminal would deploy 40 ship-to-shore gantry cranes capable of unloading a 24,000 TEU vessel in under 24 hours. The The container yard uses automated guided vehicles and stacking cranes controlled by central computer systems managing real-time logistics for millions of containers. The rail interface includes direct, standard gauge connections, moving containers from ship to train without a single truck touching them. Pure intermodal efficiency at industrial scale. Construction timeline: 10 years from first dredge to full operational capacity. But some of China's most powerful diplomatic statements in Africa aren't measured in tonnage or megawatts. They're measured in symbolism.